the array by myself. G. Hello.
No. This is yeah, it's working. It's not working. You know what's happening? You can see the sound very loudly. Okay.
Where is it?
Yeah, but
No,
I can hear on YouTube, but I don't know why.
but there is no.
Yeah, it's working on YouTube.
It's working on YouTube, but
But we
but he could. Mikhail could. Okay, in any case, it doesn't matter.
it's not a problem.
So you can listen.
Yeah.
So, what is this? Okay. So, recall the setting that I use, and there is a Hermitian invariant. There is a Hermitian invariant. Yeah, Hermitian invariant we have. Hermitian and minus Weber. So I forgot to write it down. Finally, they left. Okay, and we need. We saw that there is a Hermitian invariant of this hypergeometric group generated by these two generators that we denote by Q. There is a Hermitian invariant that is say of this hypergeometric group. To so this is somehow setting that is say, and so Hermitian group. So it has two real eigenvalues, and there are three cases. That is, a signature of Q can be plus 1 or minus 1, say minus 1, that is, say 1 1, say, that is, say 1 positive eigenvalues, negative eigenvalue. There is signature of Q can be 1 0. That is, say only so the second eigenvalue vanishes, and the third case, of course, is that both of them as Q is positive definite. Positive definite, that is says. Okay. So there are three cases, and these three cases can be described in terms of these. So we had 0, 1, infinity, 3 points on a upper half plane. On the upper half plane, and so these are, and we were studying the image of upper half plane by a mapping, so-called Gauss-Schwarz map, that is defined in the following manner. Say P1, I don't know. So it is defined as a UZ equals F1Z over F2Z. So these two hypergeometric ratio of two hypergeometric functions. That is, say, analytic continuation of hypergeometric series. So if one was up to constant equals to the Gauss F alpha beta gamma Z, and F2 it is something like 1 to the power a minus gamma, some holomorphic function. F2Z. That's, this kind of form, yeah. That is our setting, and we studied the image of the upper half plane as Z moves that moves along the upper leaf. And then we noticed that at 0, so you see at 0 it is, say maybe I can write it, it's better to write it 1 minus gamma, really, yes, 1 minus gamma. 1 minus gamma, that the turning, the angle, the argument changes. If this part, say 0, 1, if it is this has real branch, argument 0 branch, then after turning, making a half turn around 0, it will get e to the power gamma e to the power. So here we get e to the power pi I gamma minus 1, isn't it? So this kind of and the point was that at near each, in the neighborhood in each branching point, we can find bases. solution basis of hypergeometric equation. So, and base change, of course, was realized by GL2C. F1, say F1 tilde Z, F2 tilde Z, because some A, B, C, D of F1Z, F2, so that you see that branching asymmetric behavior is simply to measure the argument change in an easy way. So that is z minus 1 to the power something gamma minus alpha minus beta. There's one of them is I think that's F1. That there are two holomorphic around z equals 1, and another solution is z minus 1 times some holomorphic function in the neighborhood z1, z near. So we can take this kind of special choice of solution basis, so that to see easily the angular change. And so that is say U AU that corresponds to AU plus B, yeah, in terms of F1 tilde and F2 tilde. It is CU plus D. That is say, of course, ABCD. BCD, this is GL2C. Okay, so the upshot is that the image of this Gauss map, Schwarz map, will be a curvilinear triangle. The image of H by U, the Gauss Schwarz map, that is say UZ, imagine part of Z positive, that will be is a curvilinear triangle with sides that are arcs of a circle. In fact, in this projective geometry, straight lines and circles, we call both of them circles. That is say, the image with angles these angles were given by the change of argument of this UZ function that we can see quite easily. That is, in fact, you can use diagonalized matrix, as you see here, yeah, to measure these angles. And these angles are the following. Theta. So theta 0, at 0, the angular change must be 1 minus gamma to the power pi. At 1, it must be gamma minus alpha means beta. And theta infinity, that is the difference between alpha and beta. That is a circle of this type. If and so there are 3 cases that correspond to this classification. So let me call it the first case a hyperbolic case. This case Euclidean case. The second a spherical case. So hyperbolic case is the in the hyperbolic case. This is strictly smaller than 1. That is, say, the triangle looks like this. So this is the angle is theta 0 pi, theta 1 pi, theta infinity pi. The summation of angles, of 3 angles, is strictly smaller than pi. And Euclidean case, that is, the summation is equals to 1. That is a really plain usual triangle on the plane. That is really R2. So this one shall be embedded into some hyperbolic space. Yeah. And the third one, a spherical case, means that the summation of angles strictly greater than 1. That is, say, like this. Very fat, somehow fat. Okay, that's such kind of classification. We arrived at such kind of classification. Today, we shall analyze these cases in a more concrete description of these concrete, so far as possible. So first of all, let us restrict ourselves to consider the case theta 0, theta j over 1, the case 1 theta j over 1 is integer. That is, say theta j so j 0, 1, infinity, 3 cases. Mj some number that begins from 1. more than one. Even yes, I think that it must be. There is no. I'm not sure. Okay, one. Yes. Consider the case. Of course, alpha, beta, gamma can be not necessary of this form, but to avoid the covering mutual covering. So imagine that you have so if it is 1 over something, 1 over m, then 1 over m, 1 over m, and it does not, after m times turn, it will again produce another triangle, the new triangle there, that has no intersection, no except h, except size. But if it has something, sorry, it's pi over m, but 2 pi over 3 or something like that, what happens? Yeah, it's also good, yeah. If theta, theta 0, one of theta is not this form, then the coming back to 0 pi can have non-trivial intersection with the beginning triangle, the triangle of the beginning. And that, in this situation, we need to consider the a kind of covering of the space. And so this makes a turn, and so the moment this comes back, but there will be some such kind of intersection. We want to avoid such case to simplify the. Of course, it has such cases arrive, but to the moment we exclude such cases to simplify our argument. First of all, we want to understand how which kind of tiling or tessellation appears. So for this purpose, we consider only these cases. Okay. Now, so that is say we have 3 integer numbers. For example, in the case of Euclidean number, Euclidean case. For Euclidean case, means that we need to find out some numbers, or maybe theta j. I don't. Okay, mj, m0, m1, m infinity, such that they the summation of such that the summation of will give us 1. Such a and you understand that such kind of triple is finite. There are only finite, and there are only a finite number of such triples. And the triples can be completely classified. That is, say 2, 2, eventually I admit that it's infinity. That is, say, the angle can be 0. For example, this case, angle, theta 0. Yeah, this first case, yeah. The 1, and at infinity it has angle 0. Such case also considered. Or 236, 244, and 333. In all cases, you can easily imagine. You can easily imagine how these triangles look like, and the image of the upper half plane by this Schwarz map, and also the image of entire C, entire complex plane, because we mentioned that the lower half plane is mapped to a conjugate domain. So Schwarz map, it will map. There is a notion of conjugate with respect to circle, in the isn't it? So of course, in the case of if circle is a real line, it's simply the complex conjugate. But for the case of circle, also there exists a notion of yes, so the circle is circle as a real circle plus usual circle and straight lines. Because both of them can be, so straight line can be transformed into a circle by such kind of projective linear transformation. That is. So up to, so everything we consider up to some projective linear transformation. So we don't make distinction between them. So this is the conjugate point, that is, say, that sorry, not. It's rather, we are thinking about the u, the value of u. It is consider it as a u plane, the u plane. And if the upper half plane is mapped and a triangle inside of the circle, then the image of the lower half plane would be the conjugate of this domain with respect to certain circle. that is a conjugate. With respect to this circle, that is the image. That is the image of one side, one of these sides. Yeah. With respect to, of course, if you consider this circle, this arc, then the conjugate with respect to this side will be different. But in any case, we can recover the image of the entire complex plane. Complex plane. That is, it is image. This is this. U of z such that image imaginary part of z negative imaginary part. This one is positive. So we have quite clear understanding how it looks like. The essential point is to get this the image of upper half plane. The image of the lower half plane can be obtained almost immediately as a complex conjugate with respect to this. So, in this sense, in this situation, the complex, the image of the complex conjugate is nothing but reflection with respect to one, with respect to one of these sides. So consider this situation. Yeah, consider this situation. The first one. That is, say, the triangle we have on the plane is this. So this is the triangle. Image of Gauss-Schwarz map of the upper half plane. Okay, and the lower half plane. So consider it is real here, yeah, real valued, and consider its complex conjugate. That is, say it's also real, but further I continue turning around 1 z equals 1 in a positive way. Okay, and this. Then the angle here will be this angle with the same, but the image that we get will be complex conjugate to the upper half, the one that we obtain as upper half plane. This is absolutely the same. Oh, sorry. Maybe, yeah, I draw it in blue, the initial one, the upper half plane. Image of UZ. And this one, the lower one. This will be the UZ negative. And these are complex conjugates. in applying repetitively, for example, we have this generator 1, 2, 0, 1. We had this generator in the monotomic group. If you so here, where is it? Yes, I think this one. Yes, put it alpha as 1/2. Yes, that is say this will be alpha 1/2 and half, and yes, this will be -1. That is the 2, and this one will be 1. Yeah, that is say we have this monodromy action, and this will give us what? It is u plus 2 over 1. That is say u plus 2. It is u plane. What does it do? It does. So that is, in fact, this is 2. It's the length of this is 2, and it will give us the following. So this is, here you have u, and here you have u plus 2. U minus 2 and so on. Also you can obtain this manner. That is say this summation of union of two triangles. That is simply, it looks like a band. But you imagine that at the infinity they form an angle 0. They form it as 0. Yeah. They will fill the complex plane on U plane. This is the situation of this. So other cases, you can continue. But for example, this case is each the triangle of pi over 3, pi over 3 angle, pi over 3, and I have so this one is the image of the upper half plane will be this. Image of the lower half plane will be this. The union of regular triangles. And this parallelogram will cover entire complex plane in U variable. And you see that there is this kind of situation has been avoided. So this is somehow the situation that so this you can consider as a fundamental domain. Fundamental. So fundamental. So this is fundamental domain. The domain of the monodromy group. Group G, generated by H0 transpose and H1 transpose. There, these. Okay, so Euclid case is relatively simple. The second interesting case is spherical. The hyperbolic is the most difficult, so I will explain at the end in detailed manner. And most interesting, of course. So, yeah. I don't know where to erase. Maybe I can erase this one. Yeah. So this is a complete list. Complete list. There is no other. So integers, so that its inverse will give us 1. Pardon me? Complete list. So all M0, that's a complete list of M0, M1, M infinity, such that summation Mj, 1 over Mj, will be 1. Complete list. Please try to, you can verify it by yourself. For example, there is no 8. Huh? Can you put 8 or 9 here somewhere? No. It's too small. This contribution will be too small. Okay? That's a complete list, yes. This condition, yes. So now I pass to the analysis of this spherical case. Spherical case, that is, say, we need to find out such M0, M1, and infinity, such that they must be strictly greater than 1. Yeah. Which kind of choices we have? So this one also, this case also, spherical case also, we have complete list. Complete list, yeah. The list is the following. Because 1 over something, you see that so 1 over 3, this has no chance, no, whether it has a chance, so that it be greater than 1. So this case also give rise to I made a mistake. Okay. So the complete list is the following. Complete list is the following. So M0, M1, M infinity. The first thing that we imagine is 1 over 2, 1 over 2, and add something. 1 over n. Then it is greater than 1. Then we have 2, 3, 3. Is it true? 2 over 3 plus 1 over 2 plus, yeah. Okay, well, I finished. 2, 3, 4. Yeah, 2, 3, 4 and 2, 3, 5. So that's all. And some greater than 2. Yeah. So that's the complete list. 2 to 5, yes, 2 to 5 also nice. And what is this? So each list we can draw a triangle, isn't it? With angle So the first one, 90 degrees. And here I have pi over n. Such kind of triangle I get as the image of Schwarz map. This one is the image of the upper half plane, and the lower half plane we have the same image. So with respect to this side we can take complete conjugate. And the monodromy will give us, send this triangle to the adjacent triangle with the same shape. That is, say, the monodromy group, a group is, a group is so-called dihedral group. In this case, this case. Of course, there is a, so this part gives rise to a cyclic group. And also conjugate this, turning this slice of watermelon, watermelon side into other side. So this is so-called dihedral group. It gives it's D2N. In fact, we have, it is cyclic group of Z. It has 2n, isn't it? We need to, to turn back to pi. 2 pi over, to produce 2 pi, we need to repeat 2n times. That is a 2n. Okay? I think that dihedral group, the D2n. That is, what is semi-direct product with Z over 2 with this? Do you remember dihedral group definition of? Okay, it doesn't matter. So, yes, There to n, yes. Regular, yes. Irregular endgome. Okay. It's the same thing, yes. It's same. So if we gather this image of upper plane, then we get, it is absolutely the same. So what is this? 2? No. I need to put. Sorry. Like this. Then I have pi over 5. No. I divided pi into 5 parts. Maybe I need to somehow change this definition of polygon. That's it. And you see that it is exactly there. So the regular n gone, but it allows, yeah, it's two n gone, yeah, two n gone, yeah. Two n gone. Of course, yes. Well, yes, I have two n gone. Polyhedron. Yeah. And there is a cyclic action and also the reverse, the side. So maybe later I show you this picture. And also, the most interesting thing one is, of course, where is it? Case 2, 3. Sorry. No. 2, 3, 5. This is icosahedral group. Icosahedral group. So, in fact, it's Platonic solids. They represent Platonic solids. No, so the first one is not, but somehow Platonic solids. Yeah. Icosahedron, that icosa means that 20. 20 icosa. Ecos means ecos is 20 in Greek. The hydra, so hydra means face, like cathedral, chair, cathedral, hedra. Hedron is in singular, the hydra, plural. Yeah, icosahedral, and this is octahedral. Octahedral, that's 8 faces. Octahedral, and this is tetrahedral. 4. Two, 3, 3, tetrahedral, yeah. In any case, it's tetrahedral, yeah. So only these. In fact, this fact has been known since many years. Yeah, and maybe Plato knew. I don't know. So when icosahedra was discovered, but in any case, it is far before such kind of story. Yeah? Okay, so this is the analysis, examination, illustration by means of examples of these situations. And the last one, now the most difficult one, hyperbolic case, I shall explain in a more detailed manner. So in the hyperbolic case, so here, the signature of the Hermitian invariant is 1 positive, 1 negative. Positive eigenvalue and 1 negative eigenvalue, yeah? Signature. So like this, 1, -1, 0, 0. So maybe cosine hyperbolic. What is this? You see, maybe you want to, x squared minus y squared is something, yeah, because constant will be obtained from this quadratic form. So it is hyperbolic case, and the point is that there are several lemmas that I need to. So for the sake simplicity, let us denote SU11. It's M such that transpose of M times 1, 0, 0, 1 minus 1 M equals 1, 0, 0 minus 1. This one, yeah. This. This is the definition. Special unitary group. So our that is say our monodromy group is subgroup of special unitary group, but it is discrete. Discrete subgroup of SU11. SU11. Now, the lemma, the proposition that I want to use further is the following on this special unitary group. There is a so-called realization, real form of so there's unitary groups, and SU11, let us consider it's Lie algebra. Lie algebra of special unitary group, that is say it is some X 2 matrix. Two matrix, such that exponential of X is that. So exponential map. So it is a kind of tangent space. It can be understood as a tangent space of SU11 as a complex variety at the origin, at the near the identity matrix. Identity matrix will be 0, matrix here. 0, matrix. If 0, we put exponential 0, matrix will be 1. So this kind of well-known correspondence. And now, we see that SU lemma or proposition the following: PS projective. Projective, do I need it? Maybe I don't need it. SU11 projective after it is special linear, real special linear group SL2R that is okay. Maybe I put projective. Okay, SL2R, yeah. That is say, and such kind of relation. In fact, SU11, it seems to be complex, but in fact, it can be understood as, in certain say, real Lie group. Real Lie group. It is completely determined by this is yeah, in our situation it is quite important to distinguish the real and PSL to R, that is say SL to R plus minus 1 identity projective. Special linear group, because AU plus B CZ CU plus D is the same as minus AU. If you put everywhere minus, the result is the same. So we can after quotient. So on the level SL2R, these are different. A B C D and the minus ABC minus of ABCD. But here, in the projective, the level of projective linear special linear group, these gives rise to the same transformation. So everything now, we started from here, and this Hermitian group, after certain simple base change, we can reduce it to one diagonal matrix with 1 minus 1. So here, maybe today. So SL, okay, SU11. It is, in fact, consists of lemma. Okay, lemma. Lie group, Lie algebra of the special unitary group is consists of such matrices such that Z1 bar equals minus Z1. So let us see how it happens. So I use this this definition. Yeah, this definition. So let me simply verify that Z1, Z2, this because exponential of, so I call this as x. Exponential x, it is up to identity plus this linear part. plus higher order terms square. In fact, it is enough to look at this linear part to verify this. In fact, okay, so let me continue. Complex. What is this? So it's a kind of calculation, and how it works. Okay, so it is it takes some 5 minutes. So I leave it as a kind of exercise. So Z1 is conjugate of Z1 equals minus Z1. That comes from this relation. That is say that comes from this relation. 1 plus Z1 bar. So consider this exponential x bar t complex conjugate, then it will be the same plus z1 bar, z2 bar, z2, isn't it? And minus z1. I think so. Minus z1, yes. And then minus, sorry. No. To the moment it's still z minus 1. So it is z minus 1 bar. So this I consider conjugate, the transpose, and then conjugate. So this is this. Yeah. This is this plus. And then let them x will be the same. So this, if you write down this relation in terms of z1, z2, yeah? Then you have only non-trivial equation for z1 for which this relation must be satisfied, and z1 z2 can be any complex number, and this one shall be such that the complex conjugate be a minus itself. That is say z1 it is minus x1, so it's pure imaginary number. Right? Z1 is pure imaginary number, and y2 x2 minus iy2, so it's a complex conjugate, and minus ixy. This kind of, so x y2, any real number. So it is, it looks like I times x1, 1 minus 1, plus x2 times this diagonal part, and iy2 times 1 minus 1 we have. In fact, that is say this Lie algebra has 3 generators. Okay, So, and you remember that the SL2R, you recall that. What was how SL2R, this Lie algebra SL2R, huh? That is y such that exponential y is SL2R. Okay? Is a neighborhood of y near 0, 0, 0, plus 3. That is, it's almost 1. So what is this? This is also exercise, well-known fact, and somehow linear algebra, that it is made of it has generators as Lie algebra exactly the same. Plus x2 times 0, 1, 1, 0. Sometimes it is noted by E1, E2, E2, E3. Yes, it's E3, E2. So it is. So I have here E1, E2, E3. That is say. So this proposition. So it relies on the fact that SL. It's U. It is isomorphic to SL2R and SU11, the algebra and the complex. Yeah, even though it looks like complex, but in fact it's real. Yeah, but it has only real generators. Huh? So the multiplication of this kind of numbers, it doesn't. It's a matter of convenience. How to say this? Xc eta. So this product, this Lie bracket, with respect to this Lie bracket, this is so xc eta for all xc eta Lie algebra G. It's also, yeah, isn't it? Is it that? To see this structure. In fact, this number, whether it is, in fact, slightly yes, of course. Let me careful, but yeah. Any case, these generators of these two Lie algebras have the same generators, E1, E2, E3, as Lie algebra. So they are isomorphic, and this gives rise to, as exponential map, we can pass to this isomorphism. And this situation, so how we shall use it? How we shall use it? We shall use this fact to show that In fact, our next task will be the following: to show that these are geodesics. To show that the arcs, size of the curvilinear of a curvilinear triangles are geodesics somehow begins to write bad. Difficult to find. Nice joke. I have nice joking. Other ones are very difficult. So size of a curvilinear triangle. So in a hyperbolic case, hyperbolic. In a hyperbolic case, that is say this situation, the signature of the Hermitian form as 1, 1. Then sides of curvilinear triangles of a triangle are geodesics. Of course, circles that are orthogonal to the real axis. Circles or triangles are arcs of triangle circles that are orthogonal to the real axis. Or if we so in hyperbolic geometry there are two very famous choice of representation of upper half plane. If you as real axis, if the image of uz on as the image of uz u mapped to is on C. That are orthogonal to size. Let me in this situation we have angles smaller than pi. Let me draw something like this. A typical situation is this. So theta 0 pi, theta 1 pi, and theta infinity pi. Yeah. And so this. Oh, sorry. Theta 1. No. It's another on the. Or like this. If on the It's a triangle. Yes, triangle. Theta 0 pi, theta 1 pi, theta infinity pi. Yes. This is the image of that. Then here to here, there is a famous transformation, say V space, that is u plus I, u minus I. So this is u, h, upper half plane, will be mapped into the unit circle, unit circle with this linear transformation. As you see that, so what was it? U equals I, u equals 0 will be go to minus 1. So it is here, minus 1. Okay? And u infinity will go to, they say v equals minus 1, v equals 1. This will be the, say, VUI, right? V infinity, okay? This is V 0, okay? And u equals I, then it will be the center, the origin, yes. V of I will be the origin, yes. So such kind of, and you see that the image, you see immediately the why it is. So let me check it. Let me check it. So u minus I, u plus I, it's how it is. Okay. So u minus I, you see that equals 1 for all u, isn't it? They are complex conjugate. U, and you consider this complex number. They're the same. So on the real, their axis will go to the circle, unit circle, yes. And you see that and that's it. So upper half plane will be sent inside of this unit circle. And this linear transformation is kind of invertible. So these two pictures are somehow considered to be identical in hyperbolic geometry. Yeah. The hyperbolic geometry. So there are two unit disk model of a hyperbolic space. And this is upper half plane model. So hyperbolic space means that you need to introduce new some other geodesics. Geodesic. Yeah, geodesic, the shortest metric. So upper half model, so we will have y over dz. In fact, imaginary part of. In fact, we are in U space, so maybe it's better to write like this. imaginary part to U, du. This is the metric. No, not the metric. That's a geodesic. To measure geodesic. So Z1, Z2. So these you okay, you want to do this distance is defined like a minimum of all curves gamma U1 to U2 of this integral. This will be the distance hyperbolic distance between U1 and U2. And this, so U1 and U2, there are different types of curves that connect to U1 and U2. But in fact, so the one is minimized, and the geodesic is a circle, an arc, that part of a circle that's connecting U1 and U2. U1 and U2. So this straight line, this is not the geodesics on a hyperbolic space, and here, with respect to this measurement, yes, definition of length, say, definition of length. This one is the geodesic that connect U1 and U2. And also this one is this one, yeah. Yeah, so the if you consider edge, vertex, two vertices of curvilinear triangle, then the edge, that is, say, the image of the Schwarz map of image of interval connecting two branching points of hypergeometric function will be the by Schwarz map will be the geodesic. This is this. Between these, yeah. So, and the statement we shall look at next time will be, and also orthogonal. That is, say, this is a all orthogonal. Orthogonal. Okay. That is here also orthogonal, because this linear mapping, projective linear mapping, is a conformal map. So this is also. So this side and this side. Yeah, that's it. Okay, so next time we'll see this, the proof of this statement, because this is a quite nice introduction to hyperbolic geometry that that arises from hypergeometric function. You can take a look at this. So, yeah, this is somehow the hyperbolic space. And also I brought today a nice book by this one,